So in this next recording, we're going to continue, yet again, our fundamentals of chemistry, but we're going to take it in the direction of buffers, right? Specifically pH buffers. Right? Now, in the recording on pH, we talked about pKa. And just to review, it's the characteristic tendency of any given acid to lose its proton to solution, right? So how willing is that molecule, whatever that substance is, to give up a proton to solution and hence act as an acid, right? So again, the easier that proton comes off, the stronger the acid is. So as soon as it hits the water, it's like, oh, I'm giving up protons, and I'm pushing the concentration of protons up, and I'm making the solution more acidic. So again, that pKa is going to be a number that defines the equilibrium constant for this tendency, right? Histidine was our example before, where we see this in a protonated and deprotonated form. This is a conjugate acid-base pair, and that's really going to be the key to buffers. So if you think about the term buffer on its most fundamental level, it's something that lessens the impact, right? So if you think about your car, if you run your car into a wall, that whole front bumper and part of the car between you and the wall lessens the impact. It crunches, it collapses, it gets destroyed, and what it's doing is dissipating the energy of that head-on collision and lessening the impact that you feel. That's how cars are built. If you've ever watched a movie online, all of a sudden you say, oh, I want to watch this movie. I hit play, and all of a sudden it says buffering, buffering. Why is it buffering? Because it's lessening the impact of the variability that you're getting in your signal, right? So if it can build up enough and save enough memory in a little buffer, so it can keep playing the movie as it continues to download, then you don't get stops and starts in your movie. So buffers are something that lessen the impact. For us, right now, we want to consider the job of pH buffers, right? So pH buffers are going to be conjugate acid-base pairs. If you have a buffer present with the right pKa, it will lessen the impact of a pH change when you add an acid or base. And that's very important because biology has evolved to work at very specific pHs, right? Now, sometimes those pHs are high, sometimes they're low, depending on what compartment of the cell or the environment a cell lives in, but it is optimized, and we want to control the pH. So we do that with buffers. Now, if we look at the titration curve of a weak acid, it's very different than the titration curve of a strong acid. So this is the one we showed earlier and that you're familiar with from your chemistry courses. This is a vertical line. A slope is almost vertical as it goes to the equivalence point, right? So when I have a pH 7, protons are equivalent to hydroxide ions. It's almost on a vertical slope. But if it's a weak acid, all of a sudden, that midpoint where I'm half titrated, where my HA is equal to my A minus, the slope is almost flat. And that's really important because that means that as I add more hydroxide ion to this titration experiment, the pH changes gradually until, of course, I use up all the buffer at the equivalency point, and boom, then it skyrockets. Right? So that pKa is what's important to a buffer working well. Now, the best way to think about pKa to make it effective and useful in a biological system is think about it as the pH at which the conjugate acid and the conjugate base are at equal concentrations. Basically, this means that I have enough conjugate acid to donate protons to solution if hydroxide ions are added. Or I have enough base, conjugate base, to mop up excess protons if acid is added to solution. Right? So they're literally sequestering or releasing protons to keep the pH of the solution near the set point where you started. All right? Now, that conjugate acid-base pair is really the key. And we have examples of this in our blood. For example, carbonic acid is a blood buffer. So you look at carbonic acid, you can see the conjugate acid-base pair here. And this is going to help maintain your blood at about pH 7.4. If the pH of your blood drops below 7, you're on your way to death. As well as if it goes alkaline above 7.8, you're in bad shape, right? So maintaining that blood pH is super important. And carbonic acid is just one of the many buffers in your blood. They're going to try to maintain that pH.